হ্যালো।
হ্যালো।
হ্যাঁ, বলছি দুজন অন্য কলের মধ্যে কাকে হোস্ট করব?
আহ, যে আনমিউটেড আছে।
এক সেকেন্ড। দুজনেই তো আনমিউটেড দেখাচ্ছে।
বলবো বলো তো এবার।
একজনকে মিউট করে দাও। ওকে। যে আনমিউটেড আছে তাকে হোস্ট করবো তো?
হ্যাঁ, এবার যে আনমিউটেড আছে তাকে।
আচ্ছা, চেঞ্জ চেঞ্জ হয়ে গেল কিন্তু।
হ্যাঁ, আমি দেখলাম, আমি জাস্ট
ঠিক আছে।
বুঝতে পারছি।
ওকে, আমি এলাম, হ্যাঁ।
Hi,
Hi, excuse me. Hi,
hi. Uh, uh, you can hear me clearly, no?
I can hear you. Yes, can you hear me?
Yes, I can hear you clearly.
Okay, good.
So, uh, can you please try to share your screen so that we can check it is working fine?
Sure. Let me see. There, is that working?
Yes, it's working.
Okay.
We still have some time left, so let's wait for some time and
Yeah,
then we
sure.
will.
Sure.
Uh, Hello. Uh,
Hi.
hi. I think we can start. People join a little bit late, but we can start in time actually. Okay. Okay. So, welcome everyone to today's Majorana-Raychaudhuri seminar. Today we have Professor Paul Saffin from University of Nottingham with us, and he will be talking about path integrals, thimbles, and MCMC. Okay, sir, you can begin.
Okay, so excuse me. Thank you for organising the seminar. I'm going to talk about some work that I've been doing over a few years with different people, mostly Zonggang Mo and Anders Tramberg, but also Pete Millington and Simon Woodward. And the project really is to have a look at real-time path integrals and see if we can try and solve them. So I'll start off with a bit of motivation, why you want to combine quantum mechanics with real-time evolution. Then I'll talk about the actual problem that we're trying to solve and the method as well. So the main motivation really is just to recognize that the universe is quantum mechanical and it's dynamical as well. And so these two things are important in various settings, such as cosmology, soliton dynamics, and phase transitions. So having tools where you can study quantum dynamics, in principle, will have an impact in a number of different areas. The quantum mechanics has got a few different approaches. There's the Schrödinger approach, the Heisenberg approach, but we're going to focus on the Feynman approach, the path integral. The point being that it's really just an integral, and we kind of all know, roughly speaking, how to do integrals. So why not just try and compute the integral as we would any other integral? And but in particular, we're going to be looking at Lorentzian path integrals. So this is people have used lattice QCD to study this integral, but we're particularly focusing not on the Euclidean space, but the Lorentzian version. And there are really two main problems that you face when you do this. The first one is that it's a big integral. You have all the space-time points and all possible values of the fields at all of these space-time points, and you have to integrate over everything. So it's a huge integral, which is the first problem. Secondly, if you're doing the Lorentzian case, the integrand is a phase. So each of the IS, where S is the action, is a phase. So the integrand is rapidly oscillating, and this causes huge problems if you're trying to do this numerically. For the first thing, with it being a big integral, we've got various Monte Carlo techniques that allow you to deal with big integrals. So there's a possibility that we can get around that problem using Monte Carlo sampling. The second problem of it being a phase is, broadly speaking, what this seminar is mostly about, and it's how to deal with this sort of complicated, highly oscillatory integrand. Essentially, it's using Cauchy's theorem, but the technique is called Picard-Lefschetz, but really it's just Cauchy's theorem. And so we're going to try and describe how you can use that to make the integrand better behaved. So what we're trying to do is just to set the notation. We're trying to solve integrals like this, and it's standard notation to use this letter I. It's important to recognize that what we're doing here is not a Wick rotation. This I here is still imaginary. It's just standard practice to use to absorb the square root of -1 into this factor -I. Okay, so it might look like we're doing Wick rotation, but we're not. This I is still imaginary. So this is the kind of integral that we're trying to compute. But before we kind of dive into path integrals, let's have a look at a simpler setting where we can try and figure out what the techniques are that we're going to actually use. And to do that, we'll have a look at the Airy function. Okay, so instead of having a look at this path integral, let's have a look at the Airy function. AI is a function of x, and you can represent this as an integral. And it's an integral over a highly oscillating function, so e to the sort of phi cubed. And if you to plot the integrand, you see here that it's extremely highly oscillating as you go to large values of phi. And numerically, that means it's essentially impossible to do this integral. So the way we approach this is we're starting off here with phi being a real variable.
Sir, sorry, what is the x here? It is the coordinate?
What is the what, sorry?
X.
Yeah, so x, we're just thinking of x as some number. So imagine you want to compute the area function of some number x. What you have to do is you compute this integral for that value of x. So you just plug that number in there.
Okay, thanks.
Okay. So we're integrating over phi. Phi is a real variable, and the integrand is highly oscillating, and this is very difficult to do. So the way you approach this integral is to promote phi to being a complex variable. Okay. Now, ignore the grey region and the blue region. I'll get to that in a minute. But what we're now thinking about phi is as a complex variable, and so this integral is just the integral along the real axis of this complex variable phi. So that the integral that we're interested in, that we started off with, is just the integral in this complex plane along the red curve. Now, if you look at the integrand along this red curve, because it's e to the phi cubed, you see that it's got this, as you move along the red curve, you plot the integrand and it looks like this oscillating function. So that's the thing that we started off with, and it's very difficult to integrate. Now, these grey regions here in the complex plane, those are the directions that if you go along to infinity in those directions, then the integrand goes off to 0. So in these grey regions, asymptotically, the integrand disappears. Now, Cauchy's theorem tells you that if you do an integral along a curve that's deformed from the original one, as long as you don't go through any poles, then you'll get the same answer. But you also need the endpoints of the integral the integrand to vanish, so that you can close off the integral contour. So in other words, the integral along the red line here is equivalent, will give you the same answer as integrating along the blue curve, because we know that if you join the blue and red curve at infinity, the integrand goes off to 0. So the reason that's useful is that if we plot the function along this blue curve, then the value of the integrand, in other words, the function looks like this nice Gaussian. Okay, and that's easy to integrate. So what we're saying is we're interested initially with an integral along this red curve, but we can use Cauchy's theorem to deform the red curve to the blue curve, and in doing that, the integrand becomes better behaved, and it's much easier to integrate numerically. But Cauchy's theorem guarantees that you get the same answer for integrating this nasty red function or integrating this blue function. You get the same answer. Okay. So the next question then is, how do you go about finding these blue curves, these curves that are better for integrating along than the original? And this is where the Picard-Lefschetz approach comes in. So one class of blue curves are called these Picard-Lefschetz thimbles, and the way you find them is by looking at saddle points of the exponent of the integrand, sorry, and then from those critical points, you compute a gradient flow, right? So you find in the complex plane where the critical point is, and then you solve this gradient flow equation from the critical point, and it maps out this blue curve, for example. Okay. Now, the reason this gradient flow turns out to be really useful is the following. If you compute how the exponent I changes as you move along this gradient flow, you find that the rate of change of I is non-negative. It's real and non-negative. So this is important. This is telling you that as you move along this gradient flow curve, the real part of I is increasing. And if you look at our original integral, you've got e to the minus I as your integrand. And so if the real part is increasing, then that means you're getting a damped integration. It's getting exponentially damped as you move along the curve. So this blue curve that you get from the gradient flow of the critical point is in some sense the sort of the ideal curve, because the integrand is becoming exponentially damped along that curve. Okay, so let's have a look at an example then. We've got this area function. Let's pick some values of x and see how this works in practice. So we're interested in the area function evaluated at some number x. Let's pick a particular choice of x is e to the 0.1i. So the process is that you look at the exponent, you compute the saddle point of the exponent. So in this case, for the area function exponent, the saddle point is, you vary the exponent and you set that variation to 0 to give you the critical point or the saddle point. And so the saddle point in this example is phi squared is minus x. So you know what your value of x is, and you can find the saddle point. So if you take your x to be e to the 0.1i, then your saddle points are essentially plus I and minus I. Okay. To get the curve, the thimble, what you do is you start from that saddle point and you do a gradient flow using the equation that we just had. So you start at your saddle point here, for example, in plus I, do a gradient flow, and that fills out this curve here, which is labeled j plus I. The other saddle point down here, which is at minus I, do a similar thing. You start off at the saddle point, you do a gradient flow, and that gives you this other curve, which is called j minus I. Now, the original integration, this one here for the area function, is the integral along the real axis. Okay, so we're originally interested in integrating along this real axis here. But Cauchy's theorem tells you can deform that axis, and so we can deform the axis to this curve up here, the j plus I, and so you can integrate along the j plus I thimble curve, and that'll give you the same answer. Okay, so in this case, the thimble at j minus I is not used in the calculation. Right? That's not relevant for computing the area function evaluated at e to the 0.1i. Okay. So, we can have a look at a different value of x. Let's say x to be minus 1. Again, we go through the same process. We compute the saddle points. The saddle points are at phi squared is minus x. So if x is minus 1, then these saddles are at plus or minus 1. So the area function evaluated at minus 1 has got a saddle point at minus 1 and a saddle point at plus 1. And again, we now compute the Lefschetz thimble by performing the gradient flow from those saddle points, and you map out these two curves. You get the j minus 1 curve and the j plus 1 curve. Now, the interesting thing in this case is that in order to get an integral that's equivalent to along the real axis, we actually need the contribution from both of these curves. You can hopefully kind of see heuristically that the real axis will deform not to j minus 1 or not to j plus 1, but the combination of j minus 1 and j plus 1. So in other words, to reproduce the integral along the real axis, we need the contribution from both of these thimbles. And that's different to the case that we had on the left-hand side, where we just use one of the thimbles. So this is one of the problems that we're going to be faced with. First of all, you need to find the critical points. Then you need to find the flows from the critical points, and you need to decide whether the thimbles are actually relevant for the calculation or not. And if it turns out there are multiple thimbles involved, then numerically that's a problem with Monte Carlo techniques. What can happen typically is that when you're doing this Monte Carlo sampling, the sampling can get stuck on one of the thimbles. And if your calculation needs both thimbles or more than one, then your Monte Carlo technique can struggle to get the right answer. So resolving this was kind of one of the main reasons we had a look at this problem.
Hello, sir. One small question.
Sure.
So when we are deforming this path, so in this prescription, so is there anything that makes sure that we are not crossing any singularity or something?
Well, so it's important that when you deform the contour, you don't go through any singularity, any poles of the thing that you're integrating. But in this case, we're integrating this exponent here, and there are no poles in that function. So
yes. So in general, also it is true in this prescription, means not for only this function, in general.
Yeah, so depending on the function that you're interested in, you need to make sure there are no poles, that you don't cross any poles.
Okay.
But the kind of thing that we're interested in, physical actions like this, there are no poles. And so, so it's an important point to think about. But in the cases that we're looking at, there are no poles that are crossed. Yeah.
Okay. So another thing here, phi is real. Seems like the phi is real, no? So
Yeah.
for complex fields or something, it will be more complicated and
Ab-
like
abs- Absolutely. So if you were to start off with a complex field, you would treat that as two real fields, and then
yes.
you would make each of those real fields promote that to a complex field. So you end up with two complex fields in that case. Yeah.
Okay. Okay. Thank you, sir.
Okay. So those are the Lefschetz thimbles. There is another approach. So Alexandru and company, and so this is called a generalized thimble. And the basic idea is that you don't need to necessarily use the Lefschetz thimble. You just need to use a better contour. It doesn't have to be the one that goes through the critical point. You just need to lift the curve away from the real axis sufficiently far so that your integration is better behaved. Your integrand is not quite so oscillatory and it gets damped. And this is the idea of the generalized thimble. So the picture here is that what you do is you essentially flow the real axis itself to construct a new curve. So you pick a point on the real axis and you flow it using the same flow equation to a different point in the complex plane. So what you're doing is you're taking the flow equation, but you're giving it a different interpretation. So you're not flowing from a critical point, you flow every point on the real axis to give you a new curve. And because it's the same flow equation, it has the same properties, and so the integrand still gets damped, and you get a better behaved integration. So let's have a look at an example to see how this works in practice. And let's suppose we've got a quadratic case where the exponent is x squared. This is nice because you can solve it exactly. But what you're doing, so in this case, you can solve exactly where the Lefschetz thimble is, and it's this red curve at 45 degrees. The idea of constructing the generalized thimble is you pick a point on the axis, let's say here, and you flow it using the flow equation for some finite amount of time to another point. Okay, then you pick another point on the real axis and you flow it for the same amount of time, and that gives you another point. So you do that for every single point on the real axis, and you end up with this generalized thimble here, this blue curve. If your flow time goes off to infinity, then you end up reproducing the Lefschetz thimble. And in fact, if there's more than one thimble involved in your calculation, you would flow to the correct sum of all of the thimbles that are needed. So this is a very nice approach in that you use the flow equation to construct the your new surface, your new curve directly. Yes, so I guess also explicitly, you don't need to know what the critical points are for this because you start off with with your original integration curve and you just flow it and you get what you get. But the convergence is improved because of, excuse me, because of the flow equation. Okay, so that's the general idea. Now, what we are interested in applying it to is quantum mechanics, quantum field theory, and the kind of things that we want to compute in quantum field theory are expectation values of operators. And so what we want to do is try and massage those expectation values of operators into integrals that we recognize and can then use these techniques on. So for example, if we're looking at the expectation value of some operator O, this is then the trace over some density matrix times O, which you can write as a path integral. Right, now this doesn't quite look like the sort of integral that we're used to, so we've still got some manipulation to do to get it into the form that's that we can work with, because we've still got states and operators and so on. So we've got a bit of work to do. But the work is fairly standard. It's Schwinger-Keldysh techniques. The point is here that we have the states are evaluated at some initial time t0, but our operator lives at time t. And so the way to turn this into an integral that we can work with is to insert complete sets of states that take us from some initial time t0 up to the time t, where the operator lives, and then back down from t to t0, where the density matrix lives. Okay, so we insert lots of incomplete sets of states in between these times. So here we start off at time t0. We insert a complete set of states at time t1, which would be think of as t0 plus delta t, and then you work all the way from t0 up to the operator time t, and then all the way from operator time t back down to t0. So this is the usual kind of Schwinger-Keldysh contour approach. But it's still not in the form of an integral that we can work with. So we've got lots of amplitudes sitting inside our path integral, and so the next step is to evolve the bras and kets from the times tn and tn plus 1 to some middle time, let's say tn plus a half dt. You use that with a Hamiltonian, and then we insert a complete set of momentum states. And then that combines with the Hamiltonian to give the Lagrangian, and then we end up with this hopefully kind of familiar expression that you get from the Schwinger-Keldysh approach. So this is now starting to look a bit more like an integral. These are sort of integrals over functions, but we've still got some initial data in this initial amplitude with the density matrix. But apart from that, it looks like an integral over standard functions. Okay, so we have some integration over initial data with this density matrix, and then an integral over all of the configurations subsequent to that initial data along the Schwinger-Keldysh contour. So the thing we need to do then is figure out what we're going to do with this density matrix bit, because it still doesn't quite look like an integral that we're used to, and there are different approaches here. So let me describe one of them. We've got this initial density matrix that we need to do something with. So one approach which Alexander and company took is to take a thermal density matrix, so initial state being thermal. And the nice thing about that is that then this initial amplitude can be expressed itself as a path integral. So now the entire problem of this expectation value of the operator is in the form of an integral. We've got the integral over the full sort of dynamical part from T0 to Tm, and we've got the initial data itself also being represented as an integral, as a path integral. So you can go ahead. Now we've got everything in the form of an integral, albeit quite a complicated and involved integral. It is just an integral. So you can go ahead and use the Picard-Lefschetz techniques and Monte Carlo, those integrals that you get after doing the Picard-Lefschetz approaches, and you find what you find. The difficulty in this case is that there are many saddle points involved in computing this integral. And so the Monte Carlo computation is quite challenging, because the Monte Carlo can get stuck in different around the different saddle points, around the different thimbles, and so you need to make sure you sample them all in order to get the integral done properly. Now, physically, this makes sense because this density matrix corresponds to a thermal state. So effectively, what this path integral is trying to do is sample all of the states within this thermal state. And each one of those, roughly speaking, corresponds to its own separate thimble. And so by trying to do them all at the same time, the Monte Carlo is going to struggle somewhat. So if that's what's causing the problem, then what we really want to do is try to separate this initial density matrix part from the rest of the contour. And then we deal with them separately. The other reason, of course, is you might not want to start in a thermodynamic equilibrium, and so you want a different way of treating this initial data. Okay. So we found a convenient way to do this was to use, again, an old technique of Keldysh, which is to introduce new field is essentially new integration variables. Instead of working with integration variables phi plus and phi minus, we work with their sum and their difference. It turns out that this is quite a nice combination. It is just a change of variables, and so you can rewrite the path integral in terms of these variables. So this here doesn't represent any kind of approximation. It's still the same path integral. It's just we're now using different variables. But the nice thing about this is we kind of explicitly pull out the initial part of the path integral, which involves phi naught and phi 1. So remember, phi 1 is just the time at t naught plus delta t. So this really is just the initial data. So we have a path integral over the initial data, and then we have a path integral over the sort of dynamical part, the rest of the Schwinger-Keldysh contour. So it naturally splits up. This W itself is a path integral over the phi naught Q. And the nice thing about this representation using the phi Q and phi CL is that we can do this integral explicitly. So the integral over phi naught Q we can compute explicitly, for example, looking at a real scalar field. And when you do, you find this nice Gaussian structure. So what that's telling you is that the path integral over phi naught CL and phi 1 CL can really just be represented as a Gaussian ensemble with a particular variance given by these factors of 2n plus 1 times omega. Okay, so inside this full path integral that we're interested in, the phi naught CL and phi 1 CL we can do explicitly just by doing a Gaussian ensemble with these distributions. So the picture is that you draw phi naught and phi 1 CL from this distribution, and then you perform the rest of the path integral, the dynamical part of the path integral. And then you draw another phi naught CL and another phi 1 CL from the distribution, and you compute the dynamical part of the path integral for that, and you keep on drawing distributions from the distribution, and then you add them all together at the end. So the phi naught and phi 1 CL is an easy bit to do. The reason this turns out to be particularly nice is that for any given phi naught and phi 1 CL, there is actually a single unique critical point. And that critical point is where the phi CL is just given by the classical equation of motion and phi Q vanishes. So in practice, you draw phi naught and phi 1 CL from the distribution, you find there's a single classical critical point, which means there's a single thimble, which means the Monte Carlo approach is better behaved. So for example, we performed some calculations using this idea and had a look in a phi to the 4 theory to see if we could reproduce some results that we'd expect for an interacting theory. And here's a result. So it's a particular correlator. It doesn't really matter which one it is. All that's important is you let's just have a look at the curves. So the blue curve is the case for no interactions. So this is the free theory. The black curve is the calculation that you get with the thimble, and you see that matches fairly well what you would get from a one loop calculation. I should stress, of course, the one loop calculation itself is perturbative, whereas the thimble calculation is non-perturbative. There's also a pink curve on here, which is what's called the classical statistical approximation. Now, the classical statistical approximation is sort of halfway between a classical calculation and the fully quantum mechanical calculation. The classical statistical approximation is where you do the initial ensemble sum over initial data, but all of the subsequent evolution is purely classical. So whereas in the thimble case, the full dynamical evolution involves the path integral, the classical statistical case just uses the classical evolution. But actually that does a reasonable job of reproducing this correlator. You can also apply these techniques to tunneling in quantum mechanics. So we wanted to see how good the classical statistical approximation was compared to the thimble. And so here we ran an example where we have a double well potential. We prepare the state in the left-hand side, and then you evolve the state to see what happens. So on the right, what we've got is the expectation value of phi, which you can think of as really just being the position of the particle. And you start in the left-hand state, and you do a calculation using standard Schrödinger equation. You get the red curve, so that's the fully quantum mechanical Schrödinger equation. The thimble curve gives you the blue line, and that matches perfectly with the Schrödinger approach. But the classical statistical approach breaks down, it fails in this case. So although there are some things where you can get away with classical statistical approximation, there are some things like tunneling where you probably expect, as you might expect, it doesn't quite work. But the thimble approach reproduces the quantum mechanics as it should, because it is just, after all, the Feynman path integral that you're solving, which is equivalent to Schrödinger quantum mechanics. So more recently, what we had a look at was recognizing that now we know that for each one of these phi-naught and phi-1 pieces of initial data, we know what the critical point is. We know there's one of them, and we know what it is. It's just the classical configuration following from that initial data. So if we know what the critical point is, we could just compute the Lefschetz thimble directly, rather than working with a generalized thimble, which we did for the previous calculation. We could just work with the Lefschetz thimble directly. So the way we actually did this in a slightly different way, but the way we kind of approached this was to think of the Lefschetz thimble as being constructed as a set of rays that come out from the critical point. So here's the surface, which is the Lefschetz thimble. We know the critical point is somewhere there, and then you flow from the critical point, and the set of all of the flows generates the full surface, the full Lefschetz thimble. The direction of the flow you can get from the Hessian of the exponent, and that tells you essentially the tangent space of the thimble around the critical point. So you can map out the whole thimble as a set of rays. You have the initial direction at the critical point, and you have the direction along the flow of one of these rays, and that completely maps out the Lefschetz thimble for you. So that's fine, but when you're doing numerics, you can often come up with various problems. And it could well be that the Lefschetz thimble itself is not a particularly well-behaved shape, and so we wanted to have a bit more freedom in constructing a manifold that we could integrate on. The point being that when you use Cauchy's theorem, you don't have to go from the real axis all the way to the Lefschetz thimble. You can, again, just like the generalized thimble, you can come up with some surface in between that's better behaved, but not the actual Lefschetz thimble. And so we wanted another parameter that we could play with to construct another surface that was an approximation to the thimble in some sense, but a different surface that overall you could integrate on. The important thing to realize is that the final result is not an approximation. You're just integrating along a different surface. So what we did was, given that we know where the critical point is, we extended the tangent space at the critical point to cover a disk of some region. And then within that region, we use the Gaussian structure around the critical point to construct that flat region explicitly. And then when you come to the boundary of that region, you then use the full nonlinear equations to generate the rest of the flow. Now, it's important to realize again, to stress again, that this is not an approximation. We're just using a different surface. So this is not quite the Lefschetz thimble. It's not the generalized thimble either, because it includes the critical point where the generalized thimble doesn't. it's just a different surface that we're using, and we've got this extra parameter that we can dial, which is this R0, the size of this disk around the critical point. And the idea is that parameter R0 is going to allow us to tune our numerics to get the best possible value that's suitable numerically. If we could do this analytically exactly, then it wouldn't matter the value of R0. You'd get the same value for all R0, but numerically some R0 will give you better behaved integrals. Okay, so let's just do an example then, again, just to kind of orient what it is that we're actually doing. So here's an example of an integral. It's not a particularly nice integral, so we're after the expectation value of y to the 4 multiplied by some phase. Okay. Now, although this isn't a very nice integral, you can actually do it analytically, which is why we chose it. And all we wanted to do was to see if the sewed thimble approach would reproduce the answers that we know analytically for this particular case. And if it does, then we could go ahead and apply it to field theory. So the approach is as follows. We start off with real variables x and y. The integral with real variables x and y is not very nice because you've got this phase in the exponent. So we take the Picard-Lefschetz approach and we promote the real x and y to be complex. Then you find the critical points of the exponent. Then you can adapt the coordinates to that critical point, construct the Hessian around the critical point. That's going to give you your, the eigenvalues of the Hessian will give you the tangent space for the thimble. And then you can use those tangent space vectors to construct the sewed thimble in this inner region, the flat part, if you like. So that's all analytic. And that gives us the inner part of the integral that we're interested in, which is in this inner sewed region. That's the analytic expression for the integrand. And on top of that, we then need to add the rest of the integral along the nonlinear part of the flow. So we integrate from naught out to the end of the disk R0. This is all on the inner part of the thimble, the Gaussian part of the thimble. And then we integrate from R0 or tau naught in these variables out to infinity to give us the rest of the part. And this is the sort of full nonlinear part of the flow. Again, this is not an approximation. It's just splitting up the integral into two parts with this freedom of R0 that you use to tune to get better behaved numerics. So we can have a look at the how well this does by looking at the integrand along different ray directions. So here's the picture of what we're doing. We've got the full sewed thimble. We have some inner region, and we can parameterize the flow directions with some angle theta. So let's suppose we pick some angle theta. Here we've picked pi/3, and then we look at how the integrand behaves as you move along one of these rays. So for different sizes of disk, you get these different pictures as you move along the rays. So if you look at the medium disk, for example, the integrand in the inside part of the disk looks like this. There's a discontinuity at the edge of the disk, and then the nonlinear part in the outside is again smooth, and importantly goes off to 0. Okay. So what we're interested in, this appears inside the integral, so this is the part of the integrand. The fact you have a discontinuity is fine because we're integrating it, not differentiating it. And you can kind of see here why you might want to be able to tune this R0, because you get to move where this discontinuity is. You get to decide whether you want the peak to live inside the disk or outside the disk. And that kind of freedom allows your numerics to be better behaved if you pick the right value of R0. So as well as seeing how the integrand depends on theta, depends on the flow distance R, we can see how it depends on theta. So as you go around these different directions, what does the integrand look like? And here's some examples of different disk size for how the integrand behaves as a function of theta. And you can see that you start getting some peaks. So for a disk size of 0.1, the blue curve, you see that the integrand becomes quite peaked as a function of theta. Okay, so as you move around in this direction theta, for a small disk, the integrand becomes quite peaked. And that's potentially problematic for Monte Carlo techniques because they tend to get stuck when you're doing the Monte Carlo sampling, they tend to get stuck in peaks. For a larger disk size of 2, you see that you get the red curve. This is much shallower, so the peaks, it means that Monte Carlo will be able to deal with these shallower peaks much more efficiently. It can sample the full distribution without getting stuck. But again, this is not an approximation. When we do the calculation, we include the contribution from this disk and from the outside nonlinear region. The only reason for introducing the variable size of the disk is that it will help with the numerics. Okay, the Monte Carlo can get stuck in these sharp peaks, and so by tuning R naught, you can get a better behaved numerical problem. So for this particular example of an integral, we had a look at the Monte Carlo for these different disk sizes, just to make sure that the approach worked. And if you compare the Monte Carlo distribution in theta with the analytic distribution, you see that for each of the disk sizes of R naught is 0.1, 1.0 and 2.0, the analytic solid curve matches the histogram distribution from the Monte Carlo. So the Monte Carlo, what this means is the Monte Carlo is doing a good job of sampling in all of these cases. And so when you actually do the full Monte Carlo calculation, you find that it matches the exact result that we knew from the calculation. So the point is that this going through this example showed us that the technique works in principle for that simple case, and so we kind of went ahead and had a look at quantum mechanics. So again, it's the same sort of process as before for quantum mechanics. We introduced the Schwinger-Keldysh path. We had a look at scalar phi to the 4th theory. We have a dynamical field for each point along this path, and you plug it in and you go ahead and do the integral using this sewed thimble technique. So what did we get? Right, so here's a few plots. Let me kind of explain what's going on here. We've got two different observables, O2 and O3. So let's just focus on O2, the red error bar. So we'll forget about O3. Let's just focus on the red one. So this is one particular observable that we computed. We've got two different techniques that we've used. We've got the generalized thimble technique and we've got the sewed thimble technique. And so we're going to compute O2 for each of those different techniques. In the generalized thimble case, we have a choice of how long you want the flow time to be. And so you can do a different calculation for different flow lengths and see what you get. So for example, here is a result for a flow time of 0.2. And if you compute this observable O2, you get this red curve. If you have a flow time using the generalized thimble case, you take the flow time to be 0.4, you get this red error bar here. If you have a longer flow time of 0.6, you get this red error bar. So these three error bars on the left, these three red error bars on the left are measuring the same quantity using different flow times for the generalized thimble, and you see that they match. Okay, they're within error bars of each other, they're consistent. The sewed thimble approach, again, has a parameter that we can vary, which is the size of this inner disk in the sewed thimble. And we had a look at the size of this disk as being 0.5, 1.0, and 1.5. So these three error bars on the right-hand side correspond to the sewed thimble calculation for different sizes of the inner disk. Okay, and you can see that all of these three error bars match within each other and are consistent also with the generalized thimble case. The So that's the real part of O2. The imaginary part of O2, again, has the same pattern. These three on the left correspond to the three different calculations with the generalized thimble, and the three on the right are the three calculations using the three different sizes of the sewed thimble, and again, they all match. Okay. So we have these two different approaches, the generalized thimble approach that flows the whole of the integration contour into the complex plane for some amount of time, and that improves the integrand, but makes it better conditioned, and you get to choose how far you flow. And we've got these. We've also got this sewed thimble approach, where instead of flowing the real axis, you actually work with the critical point itself. We know where the critical point is, and so we start at the critical point and construct the thimble from there. But again, we have a free parameter, which is the size of the inner disc, but they match. So we have these two different approaches, and they're giving consistent results. So let me just wrap up. What I've tried to describe is that in dynamical quantum mechanical settings, we have this Lorentzian path integral, which really is just an integral, like any other integral we spend our days solving. It's quite challenging, but it is just an integral. But we do have these techniques now using Picard-Lefschetz approaches and Monte Carlo approaches. There are different ways of extending this. This is still very much early days within this field. Fermions have been tackled. We haven't looked at fermions, but they have been tackled, and there's some progress being made for those. I'm not aware of gauge fields having been done. They have their own complications. One of the difficulties with this approach is how it scales with dimensions. So as you increase the number of spatial dimensions, 1 to 2 to 3, the problem becomes numerically very, very big. It's quite challenging. So it's not clear whether this can be really be solved in practice. But it is still early days. There are very much more advanced Monte Carlo techniques than the ones we've used. So hopefully they can be used to improve these calculations and maybe make them practical for other out of equilibrium calculations. And I'll finish there. Thank you.
Okay. Thank you, sir, for this nice talk. So if you have any questions, please unmute and ask. Because I had a question. So it is kind of a so initially you were saying that there may be more than one thimbles, like more than one paths, where you were showing the first simple example. So so when you choose one of the paths, so is it done numerically, or means how do you select the path among the many paths possible? Like if there are more than one paths that you are showing initially.
Yeah, so you really have a choice.
Mm-hmm.
You really have a choice. So your initial path along the real axis, is quite badly behaved.
Mm-hmm.
And so you get to choose how you want to deform that contour into the complex plane. And they're all going to give the same answer by Cauchy's theorem, essentially,
Okay.
as long as you go in the right direction. But they'll all give the same answer. And so the generalized thimble is one approach. You have this sewed thimble is another approach.
Mm-hmm.
But if you come up with another idea, then that would also work as well. I mean, you could use potentially a different flow equation. You don't have to use the flow equation of Picard-Lefschetz. You could come up with a different flow equation. You just need a better curve than the real axis. So it's up to you how you do that.
Oh, okay, sir. Okay, I understand it now. Okay. And this kind of uh, these only the examples that you showed, they were like the e to the power is, so it is like a oscillatory kind of thing. So can it be used in other integrals as well, maybe which are hard to get the result of? Like mostly oscillatory things have these issues, but some other integrals are also possible, or is it just possible for this kind of exponential I integrals?
So it is set up for exponentials, but it doesn't have to be because you're looking the way you find that the critical point is the critical point of the exponent. So it is set
Yes.
up for exponentials, but
Mhm.
I don't think there's any reason why the exponential necessarily has to be of a phase type. So I think it's a wider class. But in quantum mechanics, it is of that type because the integrand is
Yes.
the IS. But yeah, I
Yes.
think that, it will be more general. Yeah.
Okay. 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 So I do not think we have any more questions. So we thank you again, sir, for this nice talk. So, and
Thank
can you please share the slides with us? We keep it in our library.
Sure. Yeah, I'll send you a copy.
Okay, sir. Thank you.
Okay. Thank you.